Alrighty. We're going to try this a different way. This is part two of the lecture series in chapter 11, Simple Harmonic Motion. Part two is the pendulum. And we're going to try doing this paper thing, which is cool because you don't need to see my face while I stare around at a screen and do whatnot. And I think this will provide smaller file sizes, and I'm just going to host them on my YouTube website. So they're YouTube site, I mean. Okay, so a pendulum. What is a pendulum? Well, a pendulum basically consists of two things. First of all, we need some sort of rigid support like a ceiling beam, and we have a string of length L, and then on the end of that string we attach some sort of massive object, and the massive object is called the pendulum bob. So say hi to Bob. Um, L, by the way, is measured from the support point here all the way down to the middle of the mass. That's important sometimes, particularly when you're doing labs. It's not to the knot at the top of the thing, it's down to the middle of the mass. And anyway, so this is a system that undergoes simple harmonic motion, which means there must be a linear restoring force. And how does that happen? Well, if you pull this pendulum to the side, from its normal location here, you bring it off to the side here. The secret is that it actually will lift up a little bit. And this height difference here between where it was and where it is now, that is the source of energy. But we said it was a restoring force. So let's talk about the forces. Let's draw a free body diagram for the pendulum bob when it's been pulled to the side. When it's been pulled to the side, it'll have a downwards force of m times g, and it'll have a tension in the string T. And those two forces are not they're not opposite each other, so they can't possibly cancel each other out. And the thing to do is to think about this in a coordinate system that is tilted in respect to the standard straight up and down coordinate system, tilted so that the tension in the string is along the y direction, and the x direction is the direction that the pendulum bob will start to move. I think we all understand if this pendulum bob is going to move, it's going to swing down this way, it's going to come down that way, just like the inclined plane problem. And what that means is that you should consider componentizing this into two pieces: a tension piece here, a part of the weight that's this way, and a part of the weight that's that way. And the part that's that way is mg times the sine of the angle, and that provides our restoring force. Um, the argument we have in the AP classes is that linear, because really it's theta that's the variable here, not x. And uh, and sine theta is linear for small angles. So I'm going to write that down here, that this is linear for small angles. And what's a small angle? Well, part of it depends on how accurate you want to be. If you want to do this to the three sig figs, you maybe 5 or 6 degrees to either side of vertical is what you want. But I would say that theta has to be for sure less than about 15 degrees. That's kind of the generally accepted thing. That means you can swing 15 degrees to one side and 15 degrees to the other, which isn't too bad. I mean, if you were swinging on a swing set, I think as a young child you might be happy with that. As a more adventurous child, you might want to exceed the bounds. And in fact, if you think back to your days of swing setting, um, there was a time when you would start to swing, and I know I wanted to get to perpendicular to the ground, and that was not possible. But after about 45 degrees, you felt like you were getting pretty high up there, and you might have felt this extra little flip, this extra little thing that happens. And that's because the restoring force isn't linear, and you spend a little bit of extra time in what feels like free fall. Um, that was a good indication of when to jump out of the swing if you were trying to do the jumping for distance thing. Anyhow, let's draw the same kind of cycle drawing that we had for the mass and spring system. And so we'll draw four of these ceiling beams here in four different locations on the paper. And we'll do exactly the same thing we did in the mass and spring system situation. We'll start with the pendulum pulled to the side, and then of course it will return to its natural position. but it'll be moving, and then it will overshoot its natural position and wind up over here. And then, of course, it will return to its natural position, but it'll be moving, and we're creating a cycle of different phases, different places, different ways in which the system can be. And um, we can mark these with what kind of energy. This has potential energy, which, as I mentioned before, is due to the fact that the pendulum bob raises up a little bit when it's pulled to the side. When it returns to its natural position, of course, it has kinetic energy. It'll have potential energy on the other side, and it will have kinetic energy on this side. I think we all know that the kinetic energy is going to be 1/2 mv squared. But what do you think the potential energy is for a pendulum? Well, it's going to be m times g times h. And h turns out to be a function of h depends on theta. Um, So, when all is said and done, we can characterize this thing in the same way that we characterized the other one, by its amplitude, by its period, and by its frequency. So let's just think about this for a second. In this case, the amplitude, and I'll go back to the green pen here. The amplitude is going to be characterized by theta, the amount by which you pull it to the side, and amplitude is measured in theta. The period for the pendulum is going to be t, and that's going to be 2 pi times the square root of something. Now let's cast our memory back to that last recording I made. I said that in the case of the mass and spring system, that it was m over k under the square root, and that you put the inertial term on the top, and that you put the restoring force term on the bottom. And then we have to think about what is causing this to happen. And it turns out that the inertial term is the resistance of this system that has a length L and a mass m to being rotated. And that has everything to do with the mass and the length of the pendulum. And then on the bottom, the restoring force is proportional to m times g, or the weight of the bob. So the inertial term is the extent and mass, and the force term is the gravitational acceleration and the mass, and the masses cancel top and bottom. This is really interesting about the pendulum. And one of the reasons why a pendulum can be used as a timing device so well is it doesn't really matter what the mass is. The only thing that this depends on is the length of the pendulum and the local acceleration due to gravity. That means a pendulum can also be used to determine the local acceleration due to gravity. And then, just to finish things out, if I go over here, the frequency will be 1 over the period. Just calculate the period and do 1 over. Um, so interesting. Okay, a couple different things. Here are some fun little stories. There was a famous question in, I believe it was Scientific American, and they like to ask questions, but then pour through the answers for the most interesting answers. And the question that was asked at this one point apparently was, given a barometer which measures atmospheric pressure, how could you determine the height of a building in New York? And so they're talking about a very tall building, like the Chrysler Building or the Empire State Building. And of course, they wanted to eliminate the obvious answer, which is to measure the atmospheric pressure at the bottom, at the first floor, and then at the top on the roof. And looking at the difference in the atmospheric pressure, you can figure out how tall the building is. So some of the other things that people suggested. Obviously, take the barometer to the top of the building and drop it off and time its descent, and you can work out from our kinematic equations first semester how tall the building is. One person said to tie a string to the barometer and to make a pendulum and to measure acceleration due to gravity at the ground level and then at the roof. And if your measurements are very precise, then you can find the height of the building from the difference. My another one, of course, that you might learn in your trigonometry class is to measure the length of the shadow of the building and the shadow of the barometer, and then you can form a ratio. I think the shadow of the building would be difficult to measure in downtown Manhattan there, but good luck to you. My favorite was go and find the building superintendent and offer to give him this fine new barometer if he tells you how tall the building is. So that was a lot of fun. So the pendulum is a simple harmonic oscillator. It has a roughly linear restoring force for small angles, and it goes back and forth in this repeating, vibrating way. It has an amplitude and it has a period. The interesting thing is that the period does not depend on the mass. Um, and that's the kind of fun thing we can talk about with the pendulum. So this is it for simple harmonic motion. You can read in the textbook the stuff in the first couple sections of the chapter, and you'll see that we've talked about almost everything there is to talk about with this guy. We're going to move on and talk about waves either tomorrow or the next day. So thanks for hanging out with me.